This is our review of Strand 2 of the SOL workbook, and this starts on page 25 of your workbook if you want to follow along there. So in SOL 7.2, you may use a calculator here. It tells you to solve practical problems involving operations with rational numbers. So it's a lot of word problems here, and as we're doing word problems, we need to look for the key words that we're going to be using in order to change the words into math. So these keywords are going to be important just to kind of review before you take your SOL. And all these practice problems that we have in this section will help you practice remembering which ones go with which operations. So you can review that list. Some steps for problem solving any type of word problem. You first want to read your problem, make sense of what the problem is asking you to solve for, because that's typically going to be what your variable will be. You're going to have to underline keywords and then cross out information that's not important. So sometimes they'll try to tell you some extra numbers in there that don't really matter for the problem and what your answer is going to be. You want to look for those keywords that are listed up here to try to decide which operation you're going to use. Then you'll solve your problem and show your work, and then check your answer and make sure that it makes sense. If you get an answer that doesn't seem to make sense, like it's really big or it's really small, or you got a negative number that doesn't make sense for a negative number answer, that's going to tell you my math might have been a little off here. I should go back and check my steps that I used. So we'll do a couple examples together. In example 1, the problem says the temperature in Madagascar was 60 degrees on Tuesday and 72 degrees on Wednesday. What is the difference in temperatures between Tuesday and Wednesday? So the question tells you what's the difference in temperatures. That's what they want you to figure out. So difference becomes that key word that we're talking about. Difference means subtract. So we're going to be subtracting in this problem. Now, the first day that they talk about is what's the difference between Tuesday and Wednesday. So you can find the difference of 72 and 60. The difference of those two temperatures is 12 if we subtract. And it makes sense that those two numbers are 12 degrees away from each other on a number line. That would be the other way to check it. If you get a negative number there, that wouldn't really tell you how far apart the numbers are because you can't measure distance in negatives. Now in example 2, it says Allie plans to go skydiving over the Grand Canyon. She will drop from the airplane at an altitude of 12,000 feet. She plans to land in the canyon around Bright Angel Campground, where her elevation will be 4,380 feet below sea level. How much distance will Allie cover during her jump? So the question is, how much distance will she cover? And the distance is going to be between the start and the end elevations. So it might be helpful to draw a picture of this for you. So we have an airplane. She's going to be skydiving, so she's going to drop all the way from where the airplane is 12,000 feet above the sea level. And then she's going to cross sea level and go down into that canyon, which then gets her 4,380 feet below sea level. So she's starting at 12,000 feet, and that's positive because it's above sea level. And then we're finding that distance between there. So we're finding the difference. So we're subtracting to figure out the difference between where she started and where she ended. Her ending elevation is negative 4,380 because she was that many feet below sea level. So then when we have a negative, or when we're subtracting a negative, that turns into plus or positive, which means we're just adding these two numbers to find the distance. And then we have 16,380 feet as that difference between those two start and ending elevations. So this makes sense because she fell that certain amount of feet from the airplane, which means she already went 12,000 feet when she fell to the sea level. But she went further than sea level. She went 4,380 feet below it. So if we add up those two distances from where she started to where she ended, that's going to make sense that it needs to be larger than 12,000 feet because she went further than 12,000. She went even deeper underground there. So we are adding there, but it's because we were subtracting a negative. As we go further into this strand, we're on page 29 for SOL 7.3, and this standard just asks you to solve single-step and multi-step practical problems using proportional reasoning. So we're going to be setting up a lot of proportions to solve these. Proportions are just two ratios set equal to one another, and ratios can be written in 3 different ways, and they're all listed here. Typically, we'll be seeing them in this fraction form, but the SOL may show you forms like with the colon or with the word to in between. So that's just something to look out for. When you solve a proportion, you need to first set it up and keep the units of measure in the same place on each ratio to match the units across. You need to remember that a unit rate has a denominator of 1, so that's like when we say she earns $11 per hour. That would just mean her unit rate is $11 for every 1 hour. So we would write that as $11 over 1. Then to solve a proportion, you need to cross multiply to set up the equation and then solve the equation. So we'll do a few examples together. In example 1, it says the Seattle Space Needle is approximately 600 feet tall and casts a shadow that is 120 feet long. The traffic light nearby casts a shadow that is 84 inches long. How tall is the traffic light? So you're going to use a proportion to help you set this up. If you draw a picture for something like this, it's helpful to see that these actually look like two similar triangles. So the height of the Space Needle was 600, and the height of the stoplight, we don't know, so that's our x. The shadow of the Space Needle was 120, and the shadow of the stoplight was 84 inches. So we can set up a proportion by saying the heights are on this side, and on the right side we have our shadows. So everything's lined up vertically. We had one fraction that had all the heights and one fraction that had all the shadows. Across here, 600 feet and 120 feet are both measured in feet, and they both came from the Space Needle triangle. So those are lined up. And then on the bottom, you have from your stoplight. So they're both measured in inches, so that's all lined up. So one method to check this is that we got a hashtag when we checked our units here, so that means that this proportion is set up correctly for us to solve. Now, once you have your proportion and it's correct, you can just cross multiply, and that's what these circles are showing you. So 600 feet times 84 inches gets us 50,400, and then x times 120 equals 120x. Then to solve this, we just have to get x by itself. Right now 120 is being multiplied by x, so we divide by 120 on both sides. So 420 inches equals x here, which means the traffic light will be 420 inches tall because that was our x value here. Now, in example 2, we have on Tuesday, 3 inches of snow fell over a time period of 6 hours. Write a unit rate that describes this situation. So we're trying to figure out if it snowed 3 inches in 6 hours, how many inches did it snow in 1 hour? Because they're talking about unit rate. So that's per hour or 1 hour. So we can set up a proportion that says 3 inches in 6 hours equals x inches in 1 hour. This is all lined up because 3 and 6 came together in the problem. X is what we're trying to solve for with 1 hour. We have all of our inches on top and all of our hours on the bottom. We cross multiply and get 3 equals 6x, and then to get x by itself we have to divide by 6 on both sides, which means our answer is 0.5 inches. So it snowed 0.5 inches per hour, or a half inch per every hour. Part of this unit talked about scale drawings. A scale drawing is just showing something that's too big or too small to be drawn the actual size. So an example of that could be a map of a state, and you're trying to find the distance between two cities. You could have blueprints for a house or a new building, an architect's building, certain things like that are scale drawings. In order to solve problems like this, we're going to be setting up proportions again and then solving them just like we did above. So in example 1, we have the Sears Tower is 444 meters tall. Charlie is going to build a model, and his scale is 20 meters to 1 inch. So how tall is the model? That means that for every inch Charlie's model is tall, it really would be 20 meters tall in real life. So we're going to use his scale factor of 20 meters to 1 inch, and we can put them right into a fraction together, and that's what this first side is. Then the only other number that we know is 442 meters. That can go on top because we put 20 meters on top. The question says, how tall is the model? So we're trying to figure out how many inches this would be equal to using that scale factor. So this is all set up correctly. We cross multiply and get 20x equals 442. Divide both sides by 20, and x equals 22.1 inches. So the model would be 22.1 inches tall. In example 2, it says a model car is 20 centimeters long. The scale is 2 centimeters equals 1 foot. So how long is the actual car? So again, on the model, the car would have 2 centimeters, and for every 2 centimeters that is measured on the car model, in real life would actually be 1 foot. So the actual car would be 1 foot for that measurement. So we set up our proportion using the scale factor of 2 centimeters over 1 foot, and then the only other number that they gave us was 20 centimeters, and that needs to go on top because we put centimeters on top on the left side. We don't know how many feet that will be, so that's our x. Cross multiply to get 2x equals 20. To get x by itself, we divide by 2 on both sides, and x equals 10 feet, so the actual car would be 10 feet long. Now, a percent proportion is similar to what we've been talking about, but it has this nice setup that we're going to follow every time. So if a problem tells you that you're looking for a percent, you're going to remember, oh yeah, percent, a whole percent is 100%. So you're always putting your percent out of 100, and that's just part of your whole. So we set up part over whole equals percent over 100. The other way you can remember that is over of equals percent over 100. So you first want to put your percent and 100 on the right side of your proportion, and then you'll find the whole number and the part number. Part goes over the whole, or is goes over of. So in example 1, it says 7 is what percent of 56? So 7 is the is part. Of 56, that's your of number. And then it didn't tell us what percent it is. It said, what is the percent? So since we don't know the percent, x needs to go over 100 because we don't know the percent here. Neither of these numbers gave us a percent sign after them, so we don't know that percentage. 7 was your is, so that goes on top, and 56 was your of, which goes on the bottom. So you're trying to figure out what percent of 56 is 7. So it's like if you get 7 points out of 56 correct on a quiz, what's going to be your percentage? Probably not very high because that's not very many right, but that's what you can use to kind of judge to make sure your answer makes sense here. So I cross multiply and get 700 equals 56x. We divide both sides by 56 to get 12.5% equals x. So that would mean that if you get a 7 out of 56 on a quiz, you get 12.5% as your score. Another example for percent proportions would be when we're talking about consumer mass, so tax, tip, and discount. So this question asks you for Xavier saved money to purchase a bike that originally cost $250, not including the tax. The store discounted the bike by 20%. What is the discounted price he will pay for the bike, not including tax? So it's saying what's the discounted price. We need to figure out how much is he saving and then figure out how much it actually will cost him then. So we don't know the part of this number. We know the original price was $250 and we know that he's saving 20%. So 20% can go over 100, but we don't know what 20% of 250 is yet. So that is our x on top out of our whole number of 250. When we cross multiply here, we get $50 equals x. That means $50 is what he saved. That's his discount. So we have to still figure out what is the discounted price he will pay. So we don't know how much he's paying yet. The bike was originally $250. If he's saving $50, we subtract 50 from that number, and then we figure out, okay, his bike is now on sale for $200, so we'd still have to figure out the tax later, but since we don't know it right now, we're just going to say he's going to pay $200 for his bike. Now, you could have some interest formula, but we didn't really cover this, so this is just kind of an extra thing. If you want to review this problem, you may, but we didn't really go over this year. Now, example 2 is also just another one of those. So that's something you can look over, but it's nothing that should be tested on the SOL.